Okay, so first one is washout. You can see the angle is less. Okay, second one is wash in. So first we'll go for the wash in. So if you use the straight wing, that is, this is the root airfoil and this is the tip airfoil. Both are at the what is it? Same incident angle. And the top view, the wing is like that. Assume tapered wing. Okay. Like that, if you take and if you draw the lift distribution along this span, you will get the curve with the black color line. Okay, because here the area is decreasing. Okay, so the lift also decreasing towards the tip section. Also, you know, there will be a side leakage flow that affects the pressure difference. So you will get this type of lift distribution curve. Is that clear? If you take just straight wing without any twist, is that clear?
Yes, sir.
Okay.
Yes, sir.
So here we are getting some loss of lift near the tip. Instead, if you go for this wash in, okay, assume this is at 0 degree, this tip airfoil is at 5 degree. Okay, so you know, if the angle is increases, CL also will increase, right? So compared to here this will produce more CL, so lift also will increase because lift is equal to half rho v square CL. So this it is like a multiplication factor. Okay, if CL increases, L also will increase. So if you use this washing, we can get the, so that is, we can compensate this loss of lift near the tip also. Okay, so instead of this loss of lift, we can get the uniform lift distribution if you use the wash-in. But mostly in the commercial aircraft, if you see, you can see here also, see, it is inclined downwards. Here also it is inclined downwards. Mostly we will use washout because even though there is a loss of lift, but the main priority is the safety. So for that purpose, we are going for the washout. I will explain. This is clear, right? Wash-in. So wash-in creates the uniform lift distribution. So it compensates the loss of lift that happened near that wing tip. This is clear, right?
Sir, sir, where is washing used?
Mostly in the commercial aircraft, we are not using wash-in. We will use only washout. Maybe in the UAV, that type of in the glider, that type of thing, we may use this wash-in. But everywhere, mostly we will use only washout. Okay, I will tell you what is the reason why, even though it produces more lift, why we are not going for that. But I will tell you in the next slide. So here, this aircraft, if you take this internal rectangular box is there, right? That is called flap. Okay, flap means high lift devices. So during the takeoff and landing, I told, right, we will increase the angle of attack. Also, we will employ these high lift devices. That is, it will be deflected downwards. So what happens? The camber is increases, so CL also increases. So along with the increase in angle of attack, we are increasing the camber using these flaps, so that we are getting further more CL, so that we can produce the enough lift. Okay. So this is the purpose of high lift devices. So the flap will be attached in the inward side of the wing, and in the outward you see this is called the control surface, aileron. Okay, using this only we can do all the maneuvers. And assume this aircraft is in the stalling angle. Stalling I told. So that is, stalling means the flow is completely separated from the leading edge. There is no flow over the wing, right? Complete loss of lift. Assume their pilot mistakenly went to the stalling angle. So now what happens? Flow separates completely from this wing leading edge. 1 minute. Okay, so assume the flow completely separated from the leading edge itself. So there is no flow over the wing. Actually, assume he mistakenly increased that angle. Now he wants to control the aircraft. But see, if there is a flow over this aileron, then only we can have the effective control on this aileron, right? If there is no flow, simply he can deflect the aileron up and down. Nothing will happen, right? Only if there is attached flow on it, then only it will be effective. but he went to the stalling angle. Assume here both sides we have the same that is airfoil at the same incident angle. This is also 0 degree, this is also 0 degree. If you move that to 14 degree, so the airfoil, the flow completely separates. So this aileron is ineffective. In that case, pilot cannot control the aircraft, so it may fail. This is normally happen if you go for the straight wing without any twist. Is it clear?
Yes, sir.
And you know, right, why that control surfaces are placed in the end, so that with a little deflection we can get the more moment, right? The distance increases, so the minimum force is sufficient to produce the moment. Okay, so the control surfaces always at the end. So if the aircraft stalls and if it is a straight wing, then this will be ineffective. The aircraft cannot be controlled. Instead, if you go for this washout wing, washout means tip airfoil will have low angle. So assume root has the 0 degree, tip has the -5 degree. Now pilot taking this airfoil to the higher alpha, mistakenly he went to the stalling angle of 14. So now what will happen? 0 plus 14. So here it will be totally 14. But in the tip, if you see -5 plus 14, you will get only 9 degree. Okay, so 9 means the flow will be attached. 14 means it is completely detached. So in that case, if you see the what is it, streamline pattern, so here it may detach like that near the root, but near the tip, still the flow will be attached. Okay, so here the flow is attached, so that we can effectively control this aileron, so that he can control the aircraft. Is that clear?
Yes, sir.
So we should not lose the control. So for that we have to maintain the attached flow near the tip. So for that purpose, we are going for the washout. Even though the washing produces more lift, the safety is very important. So we are going for the washout type. Okay. So what will happen? So assume he goes to the 14 degree mistakenly. So here there will be a separator flow. That separator flow will hit the tail. So the tail will explain the flutter, that is vibration. From that vibration, he will understand, okay, we went to the more angle, so we have to control the aircraft, we have to stabilize the aircraft. Then he will use all these control surfaces to make the aircraft a little bit stable. Okay, so that type of stall warning, we can get it. Okay, so always flow should be attached near the tip. The stalling first should occur near the root section. Is it clear? Or should I repeat?
Yes, sir, clear.
Yes.
Okay. Okay. And this is some survey. Everywhere you can see there is a twisting. So here more angle, here less angle. Overall, the twist is negative. Okay. So negative means washout. In all the commercial trade, etc., and all, we have only the washout type of wing, because safety is very important. So if you, so here if you go for the washing wing, what will happen? Even if the flight is at 9 degree, okay, here washing wing, assume this is +5 degree, okay, then this will go at stalling angle, okay, so we cannot control the aircraft, so we cannot go for the washing, even though there is a more lift near the tip, we should not go for the washing, we have to go for the washout. And this is aerodynamic testing. Simply by changing the airfoil profile, we are introducing small twist in the aircraft, that is called aerodynamic twisting. So sometimes they will use the same airfoil for the root and tip, but in few aircraft they will use different airfoils, 5 series and 4 series, like that. So by changing the airfoil, they are changing the profile. The complete twisting of the airfoil, that is aerodynamic twisting. That's it. I think we covered all the geometrical parameters. Actually, if it is the normal exam, this will be asked in 12 mark. Explain the wing geometry with its application. So you may start with the wing chord, span, aspect ratio, taper ratio, sweep angle, then diagonal anhedral, then wash in, wash out, wing setting angle. Okay, for 12 marks, we have to write it. At least every Title you have to explain for the 2 marks. Is that clear in geometries?
Yes, sir.
Okay.
Yes, sir.
No, I have taken only the major geometries. There might be a number of secondary geometries also. Okay, that you can explore further. Next one is winglets. Winglets, you know, right? Winglet.
Yes, sir.
Okay. So here, assume this is the wing tip. Okay, there is no winglets. So upper surface we have the low pressure, lower surface we have the high pressure. Due to that, I said there is a side leakage flow. Okay, and this only causes the wingtip vortices. This concept already I explained. So to avoid that, we are using this winglets. Okay, just one straight small plate at the end. So what happened? This stops the side leakage flow. So see here, without winglet, there is a big wingtip vortices. Because of the winglet, most of the flows are stopped. It is not disturbing the flow over the airfoil. Only there is a small wingtip vortices formation on the tip of this winglet. Okay, so using the winglet, we can stop the side leakage flow. Again, but there will be a small wingtip vortices from the tip, but the strength is very less compared to this side of this winglet, sorry, this wingtip vortices. So the induced drag also reduces. And here they explain, yeah. So without the wingtip, there is a large side leakage flow which causes a big wingtip vortices. But here most of the flows are deflected rearward. It cannot go into the upper surface. So here we are getting the very small wingtip vortices. So this produces less induced drag. Other purpose we are using the winglets. You see here, only there is a small wingtip vortices from the wingtips. Actually, here also we can see. Actually, they extend the flap. Here also there will be a side leakage flow, right? Due to that, there is a wingtip vortices. The flap also. But see, this is the smaller aircraft. Mostly in the smaller turbo, that is propeller aircraft and all, there won't be winglets. So this forms a bigger wingtip vortices. So this will produce more induced drag. Okay, mostly for the smaller aircraft, we won't go for the winglets. Only for the commercial aircraft, we are going for the winglets because they will try to reduce the manufacturing cost of this aircraft, smaller aircraft. So there won't be any wingtip, what is it, vortex generators, winglet, etc. and all in the smaller aircraft. And these are all the types of winglets. So first one is blended, the wing itself deflected upward, the curved one, and this is the canted one. There is a small portion at the bottom also, and this is the racked one, racked wingtip. Nowadays, all that new aircraft using this type of racked wingtip. This is inspired by the all the seabirds, seagulls and all. If you see, it will be like that, albatross, etc. and all. Mostly nowadays we are using this racked wingtip. In olden aircrafts, you can see this blended, canted, split, etc. and all. Okay. So ultimate purpose is it will stop the side leakage flow. Now you will come to that racked winglet. So if you take the normal wing, what will happen? There is a free stream flow and there is a side leakage. So this produces a big wingtip vortices. But if you use this racked winglet, that means we are attaching another one, some like a triangular portion here. So here also there will be a free stream flow, okay, on this small triangular portion, and the wingtip vortices formed only on this small corner. Okay, so compared to here also we have free stream flow, and the wingtip vortices are formed only on this sharp corner. And you may ask, this also produces same type of wingtip vortices, the smaller one. Then how it is efficient? Why all the aircrafts, new aircrafts are going for this? The thing is, see here it is deflected upward. For example, here I can show. So this is the conventional winglet. Assume this is the racked winglet. I think, yeah, here so I can show. I think. So this is the racked one. Conventional means there will be additional vertical plate here, right? So in the conventional one, only this area produces the effective lift. Okay, this will not contribute any portion to the lift. This may produce some side force, that's it. Okay, but if you go for the racked winglet, this extension portion also effectively producing the lift. Okay, so it is effectively reducing the wing tip vortices. Also it produces the additional lift because it is flat. Okay, it is aligned in the same wing direction only. So this portion additionally produces lift. Is that clear?
Yes, sir.
Okay, so compared to the conventional, we can get the additional lift also. So we are going for this racked winglets, and this is just the eagle with its winglets. Actually, this is the new design of Airbus bird of prey. So they are trying to simulate this same shape to the new design. This you can get it from the Airbus site. It is just the conceptual design. Here at only I think they are going to manufacture it. Okay, but as of now, this is the most efficient one, this racked winglet. Okay, all the new aircraft, they are going for this racked one. And previous aircraft and all, they may have the blended, split, etc. You can find it. Is that clear, winglets?
Yes, sir. Yes.
Okay. The next V formation of birds, this most of them may know. You know the reason, right? Why the birds are forming V or inverted V or W or M shape? What is the reason? Okay. So almost all types of bird, they try to form the V, okay, or inverted V, or like slant lines. Okay, this type of shape it will try to form. Almost all the birds. And the reason is, already I told you, for the finite wing, there will be a wing tip vortices. That means the circulating flow, right? And if you see the flow component next to the wing tip vortices, so here it will be upward. You can see this flow component diagram. So this how it is rotating, right? So outside it is upward, inside it is downward. Here also, here it is downward, here it is upward. Okay, so outside this wing tip vortices, there will be an upward flow component that is called upwash. And inside this, that is right hand side, if you take, there will be a downward flow component like this. This we are calling as downwash. Is that clear? Upwash, downwash. This is the finite wing. Assume the wing tip vortices are formed like that. Okay, so in this region, if you check, we will get upward flow component, and in this region, if you check, there will be a downward flow components near to this wingtip. Okay, so that upward flow component we are calling as upwash, and this downward flow component we are calling as downwash. Now, what happens if some other bird is flying in this upwash region? That bird will get the additional upward push. Okay, see here, this bird is flying in this upwash region, so this will get the additional push. So with less effort, it can get easily the sufficient lift, so it can fly for the longer distance. Okay, this side also, one bird is flying in this upwash region, so it is getting additional push in the upward direction. So the migrating birds mostly will form this V and inverted V formation, so that total birds and all can go for the longer distance. Once it gets tired, then it will come to the second position. Another bird will take to the lead position. Like that, keep on, it will change its position so that it can go for the longer distances. Okay. So this bird flying in the upwash of the first wing, and this bird flying in the upwash of the second wing. Like that, it is flying. Once it gets tired, this may come to the first position. Like that, it will interchange its position, so that it can go for the longer distance with a less effort. So they understood the aerodynamics better than us. So is that clear?
Yes, sir.
Yes, sir. Yes, sir.
Okay.
Yes, sir.
So this is the reason for the V formation of birds. Then high-level devices. So I already told you, the name itself indicates these devices increases the CL. Okay, for the purpose only we are using these high-level devices, and it is totally different from the control surfaces. You should not confuse with the control surfaces. So if you take that aircraft, so this is the rudder, aileron, elevator, etc. and all is the control surfaces which used to control the aircraft. But this flap, here you can see one rectangular portion, right? That is leading edge slat. Okay, these things and all the high lift devices. It is to increase the lift. Using that, we cannot control the aircraft. It is only to increase the lift. So it is called as high lift devices. Okay, so don't confuse with control surfaces and the high lift devices. So what happens? Mostly we will use the flaps or leading edge slat. Okay, these two only maximum will use it as high level devices, flap and slat. Flap can be in the trailing edge or sometimes it may be in the leading edge, but slat always will be in the leading edge. Okay, totally two types, flap and slat. These are all the high level devices. The flap can be in the end, sometimes it may be in the leading edge also. Okay, so the main idea, of this flap is, if you deflect a normal in the cruising time and all, it will be in its original position. Only during the takeoff and landing, we will deploy this. So we will deflect this. So once if you deflect that, and now if you try to draw the camber line, this will be your camber line, right? So the camber line means a line which divides the airfoil equally. So by deflecting this, we are increasing the camber. Okay, so previously this is the airfoil, this is the camber line, this is the con line. The distance is the camber. Only this the small camber we have now. So this is the chord line. The line joins leading edge and trailing edge, and this is the camber line. Distance between those two things is the camber. So by increasing the camber, we are increasing the CL. You know, right? Instead of the flat surface, if you place some curved surfaces in the air, this will get more pressure difference and more lift, right? Even you can check it in front of the fan. If you make your hand like the curved one and keep it, you will get the more push. Okay, so by increasing this curvature, they are increasing the pressure difference and lift. That's the main idea of the flap. Both flap and slats are used to increase the camber. That's it. So everywhere it increases the camber. Okay. So camber is the distance between camber line and chord line. Okay, this is the camber. So everywhere it increases the camber compared to the original airfoil. Is that clear? In the 2 marks, if they ask high lift devices, we have to write mainly flaps and leading edge slats are used, and both are increasing the camber so that we can increase the lift. That's when you have to write it. So you should not say the area is increases. You see here, initially this is the area. After deflecting also, it may be equal or less than that. Okay, so these flaps will not increase the area. Here also, if you see, even though it is extended a little bit, there is a gap. The overall area, if you see, it is not changing, the same area. Okay, almost all the flaps, it increases only the camber, not the area. Only this fowler, if you take, this is extending outside. Only this is increasing camber and area. Okay, this fowler. Other than that, generally all the high lift devices, it will increase only the camber, not the area. Is that clear? Should I repeat?
Yes.
Okay. In the previous years of the student simply will write flaps increases the area and lift is increased. That is wrong. Almost all the flaps increases the camber only. Don't forget, it increases the camber. Only this flap is a fowler flap is exceptional. This increases camber, also the area. Okay. and these are all the different types.
Sir, sir, I have a doubt. Sir, in every case, we are increasing the camber, but why are we using different types of flaps?
I will tell you. Each don't produce the equal amount of increase in lift. Each one has its own advantage. Compared to this plain flap, this produces more drag. Double slaughter, triple slaughter and all. That's what I am coming on the next slide, that only I am explaining. So this again, these are all the different types of flaps. This is plain, this is split, this is slotted. That is difference between slotted and plain is there is a small gap. Okay, there is a difference. Split is totally different. So only the lower portion of the airfoil is splitted. Okay, and this is fouler. The lower portion is extended, also deflected, and like that. This is different. You see, gurney flap. There's a small vertical plate attached in the trailing edge. What happens? This creates some low pressure region behind it, so that sucks the separated flow. Okay, that's how it increases. Also, it increases the pressure here, so the pressure difference also increases. And this is the drooped leading edge. That means the original airfoil will be like this, right? And the certain portion of the leading edge is tilted downward. Okay, this is the normal airfoil. Drooped means this portion will be deflected downward. This portion, that is called drooped. Like that, n number of methods are there. In that, mostly we are using this plain single slotted, double slotted. In the commercial aircraft and all, if you see the smaller aircraft, initially they went for this plain. You see the total CL you can achieve, it is 2.25. But in the commercial aircraft and all, maybe in the medium size aircraft, medium means maybe 100 seat, less than 100 seater, or if you take the turboprop engine aircraft and all, it will use the single slotted. That is, there will be a small gap in that. By using the single slotted, you see, compared to that, actually both flaps are deflected at the same deflection angle. But compared to the flap, the single slot produces more CL. And if you use double slot, again the CL is further increased. Okay, so in the smaller aircraft, we will use plain. Medium aircraft, we will use single slotted. In the normal transport aircraft and all, we will use the double slotted. Maybe in the cargo, etc. and all, you may further see the triple slotted also. Like this also, triple slotted airfoils also there, wings also there. Okay, so these are all only flaps. But in the commercial aircraft, addition to the flap, we are using the leading edge slat also. Okay, so here you can see this is the increase in camber. Now here you see from here to here you have to draw. It is further curved. Okay, so from 2.6 to 2.7 it is increased because of this leading edge slat. And from here you see from 2.8 to 2.9 it is increased. Okay, so I'll explain why it increases. So for the smaller aircraft, we are using plain, and for the medium size transport, we are using single slotted, and commercial transport, double slotted, cargo and heavy aircraft and all, we will go for the triple slotted. Is it clear? This is the most used high load devices. Is it clear? Am I audible?
Yes, sir, you are.
Okay.
Yes, sir.
You can also, if you traveling in that aircraft, in the way through window, if you see, mostly there will be a double slotted flaps in the commercial aircraft. If you observe, you can find it. So using this video, I like to explain why this slotted flaps produces more CL compared to this plain flap. That's YouTube video. I think video is not, audio is not required. Actually, it is of 10 minutes, but we can directly go to that last portion. Is it visible, this video?
Yes, sir.
Okay.
Yes, sir.
Okay, so this is the split flap. Okay, so a split flap produces more drag compared to the normal plain flap. You can see the wave thickness. Oh, sorry. Okay, see here the wake thickness is less because of the split flap. The wake thickness is more. So this split flap produces more drag, even though it produces equal amount of increase in lift compared to the plain flap. We should not go for the split flap. So in all smaller aircraft, we are going for only the plain flap. And here they explain the single slotted airfoil. You can see what happens to that single slotted. You can see there is a small gap, right? Through that there is a flow. So this is like accelerated flow, so that the flow is attached on this flap also. Is clear, right? So there is a flow through that gap between that is called slot. Okay, so there is a flow through the slot, so that makes some attached flow on the flap also. So now see overall wake thickness also reduced. But if you go for the plain flap, see here, there is no flow through this. Okay, so the flow is completely separated in the airfoil near the leading edge portion itself. From there itself, it is separated. So there is a large wake region. But here, if you see, here also there is the flow over the flap surfaces. So here we have the less wake thickness and less drag. Is it clear? Slatted flaps.
Yes, sir.
Okay, for that purpose only, in that transport aircraft and all, we don't go for the plain flap. We go for the slotted flaps, so that we can get the attached flow on this flap also, so that we can reduce the wake thickness and drag. Okay, let's play. Now see more wake. Now see the flow is attached on the flaps, so less wake thickness. So this is for the flap. Now they are showing the leading edge slat, how it is further increases the lift. This is how we will deploy the leading edge slat. Actually, all these flap, slat and all, it has to be used only at the high angle of attack. The low angle of attack, if you use it, it will unnecessarily increase the drag. Okay, so that's why in the cruising, we don't use this flap, slat and all. Now here also you can see, so there is a flow through this slot, that is gap between the slat and the airfoil. Okay, that gap is called slot. There is a flow through the slot. So you can see the extended attached flow on the airfoil. Now see they are closing that slat. Now the flow is straight away separated from the leading edge. Okay, but if you open that, there is a flow through that slot. So the flow is attached up to around 25%. Is that clear? You can see now it is fully separated. So here actually they just straight away extended. Sometimes they will deflect this flap a little bit down also to increase the camber. Is it clear how the slot leading edge slat works? SLAT slat. Okay. So yes, the same. Tell me more. So if you use this leading edge slat with a slot, that is gap, you can maintain the attached flow on the aircraft. So if you can maintain the attached flow, lift automatically will increase, right? Also, mostly this leading edge slat, they will deflect it downward, so that they will increase the camber also. Is it clear? So this is plain flap, more thickness, more wake, and if you go for the split, it will further increase the drag, even though it produces same increment in lift as the plane, but this will produce more drag. So we don't go for the split flap. Mostly we'll use the slotted airfoils, because through the passage there is a high energy flow, so that we are getting the attached flow on the flap also. So we are getting the less wake thickness. This is single slatted. There may be a double slatted, triple slatted also. Similarly, flap also, there is a passage, through that we are getting the high energetic flow, so that the flow is attached up to certain distance on the airfoil. But low angle of attack, if you use that, you will get the more wave thickness. Okay, it will unnecessarily disturb the flow in the low angle of attack. So in the cruising condition, we should not use this flap slat and all. Only at high angle of attack we have to use it. And here they explain, for example, transport jet. If you take the normal airfoil, maximum it can produce only 1.8 CL. Okay, but in here this is takeoff, this is landing dimension. Normally, compared to the takeoff, landing, the deflection angle will be more. Another table, yeah. So you can see almost all the commercial aircraft, they are using single slatted or double slatted. The smaller aircraft means plain flap. Only these three will be maximum used. Okay, and compared to the takeoff, landing, we are deflecting that flap to the maximum angle. Okay, because while landing, the velocity will be very less, so we should not go for the higher velocity, otherwise we cannot land it properly. So velocity is very less. So in that case, we need more lift to sustain that aircraft in the air. So we are deflecting the flap also to the more angle. So takeoff 20 degree means during the landing, this is deflect to 40 degree. That's why you see here. So takeoff CL is increased to 2.2. So the normal airfoil is 1.8. Because of assume 20 degree deflection, the CL is increased to 2.2. And in the landing, further it is deflected downwards. So it is further increased to 2.8. So this is the CL. Like that, we are increasing the CL. Once if we increase the CL, lift also will be automatically increased. Okay, this is like a multiplication factor. If increases, this also will increase. Is that clear? High load devices. I think we crossed the time. Hello, am I audible?
Yes, sir.
Okay. This is the 1 minute. This is the heavy aircraft. You can see the triple slotted. Okay, triple slotted flap. In the heavy aircraft, you can see this type of flaps. Now tell me, someone is asking. What is it? Hello? Hello? Someone called, sir. What do you want? Hello? So here there is a flow through this. So this gap is called slot. Okay, this gap is slot, and this is slat. Leading is slat. The gap is slot, and this is flap. And again, this is also slot. Okay, so if you use slatted flap and leading edge, there will be a high energy flow on this gap also. So that maintains some attached flow on the airfoil and flap, so that we can reduce the drag and we can get the more CL. That's the idea of the slot introduced in the flap and slat.